Good afternoon, good evening, everybody. Hello, and welcome to our March Engineers Inside Group webinar series. Welcome to those of you who are joining us for the first time, and welcome back to those of you who have been attending our webinars before. I can see some familiar names. It's wonderful to have you guys back. It is my honor and pleasure to introduce our today's webinar speaker. We are joined today by Lidia, who is actually a co-chair of the Engineers Insight Group. Lydia is going to talk about her work in all things space, all things aerodynamics for spatial aircraft and Martian environment. But if I was to take a bit of a step back and actually introduce you to Lydia and her background, let me do a proper job. Let me do that. Lydia has completed her PhD in aeronautics at Imperial College London, and she holds an MSc in Advanced Computational Methods for Aeronautics from Imperial College London, and also a Bachelor's in Engineering in Aerospace Vehicle Engineering from Polytechnic University of Catalonia in Spain. Her research focuses on computational fluid dynamics, aerodynamics, and shape optimization, with a particular interest in planetary flight. She's currently working on optimized rotor blade airfoils for Mars Photocraft in collaboration with Rom's team at NASA Research Center and the Mars Wind Tunnel team with a university in Japan. Lydia is also a volunteer with Flight Crowd and a co-lead for our Engineers Insight Group, as I've mentioned. Now, there were a lot of very clever words in that bio of yours, Lydia. I'm probably going to embarrass myself. I'm going to continue talking for much longer. I'm going to hand over the mic and the stage to you. Lydia, the time is yours. Please share some of the incredible work that you've been doing. And guys, for the rest of you in the audience, please feel free to put any questions in the chat. We'll be able to have some time at the end of the session to have a good discussion with Lydia and see if she can answer some of your burning questions. But in the meantime, Lydia, over to you.
Thank you, Maria. Thanks for the introduction, and thank you for all the great work you do at Flight Crowd. So, hi everyone, and thank you so much for joining the first session of the Flight Crowd Engineers Insight Group webinar series. It's a pleasure to be one of the hosts of this webinar series and to launch it today. We are very excited. Oh, let me see, why can I not change slide? No.
I think you're now in the laser setting, and then probably you can.
Okay.
Oh, I can see. There we go. There we go. It's all working.
Okay. Yeah, let me try this. Sorry about that. So the aim for this webinar series is to connect engineers, researchers, and students, and to learn from people, our invited speakers, working on the future of flight. The format will be monthly webinars with 30-minute sessions, 20-minute talk, and 10 minutes at the end for questions. So prepare your questions. And today's speaker is me. I'm going to be talking about my research. And please save the date for next month's speaker, because we're honored to have Richard Brown from Sofodine, which I think he was going to join today's talk as well as an attendee. So let me start with my talk, which is about aerodynamic design of blades for Martian helicopter, which is the research I've been working on. But before that, I'll explain a bit about my career path. So I'm from Barcelona in Spain, and I did my bachelor's there in aerospace engineering. And there is where my interests grew around aerodynamics and fluid dynamics. And then I moved to London in the UK for a master's specialized in computational fluid dynamics. I will tell you more about that later. And also I did a PhD at Imperial College London, and for the past few years, I've been a postdoctoral researcher at Imperial College London, working on aerodynamics of Martian helicopters, which was also my PhD topic. So why explore Mars with helicopters? Today, most of Mars exploration is done with rovers, and rovers are very powerful, and they have done amazing things for many years on Mars. But they are also limited. They move very slowly. They struggle to reach rough terrain like craters, and they can only explore small areas around the area where they landed. Helicopters can help with that. They can fly over obstacles, reach locations that are inaccessible to rovers like craters, like canyons, and they can scout the terrain for rovers and also for future Mars missions like scouting for new landing spots. And for this reason, NASA sent the Ingenuity helicopter in 2020, and it did the first powered flight on another planet in 2021. So it was a very successful mission. And the whole purpose of Ingenuity was to be a technology demonstrator that we can fly on Mars. And it was a huge success. It flew for 3 years, and it paved the way for future helicopters. Sorry. But flying on Mars is very, very challenging, and this is because of the very thin atmosphere on Mars with a very low density, around 1% of the density on the Earth's surface. So it's much harder to generate lift. With much less air to push yourself up, the helicopter struggles to generate lift. So to compensate, we need helicopters with larger rotors, but this is limited by the aeroshell in which these helicopters are sent to Mars. And also we can make them spin faster, but this is limited by the lower speed of sound on Mars, which limits the speed of the blades due to the compressibility effects. So we want to avoid having shock waves on the blade. So these things combined create a very unusual aerodynamic regime on Mars, which is a low Reynolds number and a moderate to high Mach number. The Reynolds number is a number that balances that represents the balance between inertial forces and viscous forces. So the Reynolds number at which helicopters fly on Mars is much lower than the Reynolds number at which aircraft and rotorcraft fly on Earth. So the viscous effects are much more important, and because of this, the flow separates easily. And the Mach number is the ratio between the velocity and the speed of sound. So with lower speeds of sound on Mars due to the atmospheric composition and the very low temperatures on the surface of Mars, and because we need to rotate the blades faster, we reach Mach numbers that are high, well, moderate, especially at the tip of the rotor, which is where the velocities are highest. So this makes compressibility effects important, and also there's a risk of having shock waves, which is not favorable for the aerodynamics of the blade. And here on the right, I'm showing a plot with different Reynolds numbers in logarithmic scale and different Mach numbers. And each of these circles is different flow conditions that we can find on Earth, from dust particles, insects, birds, and then aircraft. So as you can see, the Mars flow conditions don't overlap with any of these flow conditions. So that's why it's very unusual. And actually, we cannot take advantage of all the years of research in aerodynamics for Earth. It's very new for us. So a bit about Earth aerodynamics. So aircraft aerodynamics, as I said, they're at high Reynolds numbers. And at these high Reynolds numbers, we have a turbulent boundary layer, which helps the flow stay attached and to be streamlined. So this is a usual conventional airfoil for an aircraft wing, and the flow tends to stay attached. And the lift comes from the pressure difference in the vertical direction around the airfoil. So in this regime, we tend to try to avoid flow separation because flow separation reduces performance. Instead, at the low Reynolds number, which is at which insects fly on Earth, we have laminar boundary layers, which cannot sustain large pressure gradients, so the flow separates very easily. And so here I'm showing the wing of a dragonfly insect with different cross sections. So these are the airfoils of the dragonfly wing. which are very thin and very corrugated, very different to the airfoils that we design for aircraft. And what this does, what nature has evolved for these airfoils to do, is to have separated flow because it's laminar, so it will separate, but it separates and creates these vortices that are trapped within the corrugations, and this creates areas of low pressure which help generate lift. So now coming back to Mars. So actually Mars helicopter aerodynamics resembles insect flight more than aircraft aerodynamics. So if we use conventional airfoils like the ones on aircraft, at these low Reynolds numbers, because of the laminar boundary layer, the flow separates and they lose performance, especially as we increase the angle of attack. So instead, what research in this field has shown is that sharp leading edge airfoils perform much better. So here I'm showing an airfoil with a very, very sharp leading edge. And what this does is it makes the flow separate at the leading edge, and then the separated shear layer undulates due to the Kelvin-Helmholtz instability, which generates these vortices that roll on the upper surface of the airfoil. And these vortices have low pressure cores, so on average, they generate lift. So now that we know that we want sharp leading edge airfoils for Martian helicopters, how do we design these airfoils? And to do that, we can either do experiments in a wind tunnel, but when wanting to test Martian airfoils, we need Martian atmospheric conditions in the tunnel, and this is very, very difficult to achieve. There's only one wind tunnel, Martian wind tunnel in the world, in Japan. And if you want to test new airfoil shapes in this very unexplored regime, you would need to manufacture these airfoils, which is very expensive. So instead, what we can do is run numerical simulations. We call this CFD, computational fluid dynamics, where we solve the equations of the flow around the airfoil or wing to assess the performance. And in my work, we're using direct numerical simulations, which is solving the equations of the flow without any modeling. And so when we run simulations, we usually validate them against experiments in the wind tunnel just to check our setup represents the actual physics of the flow. And then once the validation is done, we can test many airfoil shapes. It's much easier to make this with simulations. And also from the simulations, we obtain a lot of data that we can post-process, and it helps us understand a lot the flow physics, especially in this unexplored regime. And both of these have their limitations. The limitations of the experiments is usually the blockage and wall interaction in the tunnel. And the limitations of numerical simulations is usually that we have idealized flow. So for example, the oncoming flow is usually very clean and uniform, which is not the reality when we are flying aircraft or helicopters outside. So now I'm going to go a bit more into my work. So we started our study by validating our setup in our CFD, and we used experiments that were done in the Mars wind tunnel in Japan for a triangular airfoil like this one. And here on the right, I'm showing the experimental results with the line in black, and I'm showing the lift coefficient as a function of the angle of attack, the angle at which the airfoil or wing is placed. So we started doing two-dimensional simulations, and for low angles of attack, they're not too far from the experiments, but for high angles of attack, they over-predict the lift a lot. So what we did then is to solve the three-dimensional flow. So we let the structures develop also in the span-wise direction. And at the sides of the, so we do this for a fixed span length, and at the sides of the wing, we have periodic boundary conditions. So it's like having an infinite wing, which is actually what the wind tunnel also aims when they test an airfoil. And we got closer to the experimental results, but still there was a gap in between. And to understand why, what we did is to run a simulation where we simulated the entire test section of the wind tunnel. We call this the virtual wind tunnel. And we're simulating the four walls of the wind tunnel with the size of the wing like equivalent to the wind tunnel. And these are the results, the red line. So we got much, much closer to the experiments. And this is because in this new simulation, the virtual wind tunnel, we are accounting for the blockage effect in the wind tunnel and also the boundary layer at the sidewalls. And this boundary layer at the sidewalls interacts with the flow over the wing, as you can see in this visualization from our virtual wind tunnel. And we can see this as well from these pressure distributions. This one is from the experiments and this one from the simulations. And so the flow is coming here from the left. And you can see the walls are here on both sides. And you can see that the wall is affecting the pressure on the wing. And that is, of course, affecting the lift. That's why we saw a different lift compared to the infinite wing. So now that we validated our solver and our setup, we can find new optimized airfoils. And what we did in my research is to create an optimization pipeline where we varied the airfoil geometry. In this case, I stayed with the triangular airfoil because it's the case that I validated. And also it was an easy case to do a proof of concept because to modify the geometry, you only need two design variables, the coordinates of the apex of the triangle. And the objectives of this optimization were to maximize lift and to minimize drag. And well, to run this optimization, I had to automate the whole process, which involves a mesh and automating the solver around each of these shapes in order to extract the aerodynamic forces, like the lift and the drag. So the optimization results from that optimization are shown here. So we compare them against reference airfoil, which is the airfoil that was tested in the wind tunnel and we validated against. And as you can see, the optimum airfoils are much thicker and their position of the chord is closer to the trailing edge. And thanks to this optimization, we obtain, this is lift and this is drag coefficients. We obtain much higher lift coefficient and drag coefficients. And these are a set of optimum airfoils that we found, which correspond to these geometries here. And from the results, we saw that all these optimal triangular airfoils exploit the leading edge separation with vortex roll-up that I was explaining at the beginning. We divided the whole set of optimum airfoils into 4 different groups. You can see more about that in the paper that we published. And yeah, we saw that they were all having these roll-up of vortices. But actually also the reference airfoil had separation from the leading edge, although the flow looks a bit more chaotic. So why are these airfoils optimum? So if we look at so here I'm showing the pressure coefficient on the surface of the airfoil. So the lines on top are the pressure coefficient on the upper surface of the airfoil, and these are the bottom surface of the airfoil. And what we want is to maximize the suction or the pressure difference between upper and lower surface to maximize lift. So here you can see that we have negative values on top to show the suction. So we want to maximize suction. And what we can see is that compared to the reference airfoil, which is in black, we achieve much higher suction for these airfoils. I should have said before that this optimization is done for an angle of attack of 12. And if you look at these airfoils, what the optimizer is trying to do is to place the first upper surface almost parallel to the flow to maximize the vertical force, and also to keep the vortices. Here I'm showing time average velocity contours, and this pressure coefficient is also time average, so we don't see the effect of the vortices. So also they're trying to have the vortices as close to the surface as possible to to create this area of suction, which is not happening for the reference airfoil. And then in another work that you can look into more detail in our third paper, we looked at how these optimized airfoils behave under different flow conditions. So this is related to the limitation I was talking about earlier in simulations. So we noticed that these optimized airfoils had very coherent structures, and we wondered if these would still be optimal when testing them on a real helicopter wing where the incoming flow is perturbed. Like, would these coherent structures still be there? And so what we did is to put some free stream perturbations in front of these airfoils to see what happens, and it actually breaks down the flow. So they are not that optimal when we have perturbations. And then what we did is to optimize with these free stream eddies, and we achieved different new geometries. And now I'm going to talk a bit about our latest work, which has been in collaboration with NASA Ames and Nagoya University in Japan. So this is all the teams combined. And here on the picture on the left, we went to visit the Mars Wind Tunnel in Japan, which was very, very exciting and very interesting. And on the right, we are at NASA Ames. We saw the facilities where they test the entire rotor. They have a facility where they can have Mars conditions to test an entire rotor. And what we did in this collaboration is to test first the airfoil that was on Ingenuity, the helicopter that was sent to Mars. And as you can see, this airfoil is actually quite conventional. It looks like conventional airfoils. And we tested also a new optimized airfoil by NASA, which, as you can see, has a very sharp leading edge and is very thin. And it has these aerodynamics that we were talking about earlier with the separated flow at the leading edge and the roll-up of vortices. So we studied both airfoils with 3 different methodologies: the experiments at the Mars Wind Tunnel, simulations by NASA, and our independent simulations at Imperial. And after doing this study, we saw that across all methodologies, the new optimized airfoil performs better. And you can see more about this work in these published papers. And improved performance of new airfoils, what it means is better rotor efficiency, which can allow for higher payload, which would allow more science equipment. For example, a drill to get rocks from a wall of a canyon, which a rover cannot get, or maybe some measurements at different altitudes in the atmosphere. So it can allow a lot of new science output. And also, of course, it can increase the flight range. So it overall enables more ambitious Mars science missions. And this is all. Thank you very much for your attention, and I'll be happy to take any questions from the audience.
Oh, brilliant, Lydia. Thank you very much. A round of virtual applause. Thank you. This is very, very technical, and I appreciate I've seen in the chat we have some PhD students or apologies, PhD graduates. I know we also have some recent graduates with aerospace engineering background, and current students as well. I can recognize it in the chat and in the participants. I know that we also have some currently some college and university students as well. Sorry, college students and school students. So I think we're very much covering a whole breadth of individuals with a range of different backgrounds. So I thought, in terms of questions, I also wanted to ask some questions. I thought we'll try and kind of make sure that we're covering what might be of interest to all of our different audiences, but also with about half an hour or so to go before we finish. Please, guys, feel free to drop some messages and some questions in the chat as well, and we'll come to you in a moment. But Lydia, from first one from me, if that's okay. How tell us more about you. Let's start with how did you get to where you are? It seems like you're working on some absolutely incredible research, technology, and things that will truly shape the way we live and the way we see the world and space. How did you get to where you are? Walk us through that journey, especially kind of maybe the school era as well for those in the audience who are currently
I cannot
interested.
hear you very well. I hear you very low, but I think you were asking me how I got here.
Yes, yes. Talk us about your
So,
career. Tell us about that.
well, as I said, it's been a set of steps. Like the bachelor, there I did some projects that showed me what my interests were, which was around CFD. And then I went for the master's. The master's was a great opportunity to meet incredible researchers at Imperial, and also it allowed me to pursue the PhD. So my master thesis supervisor offered me the PhD after starting the master thesis on the same topic and seeing there was potential on it. And then the PhD has been great because I gave a talk at the very beginning of the PhD about my work. I was very, very nervous. And my supervisor sent the talk to the people at NASA. I didn't think they would be, I don't know, that they would have time to look at it. But they did, and they came back to us, and they were very interested in our project, and that's how our collaboration started. Also, I went to a conference. Conferences are very, very important, and there, thanks to a mentor and now friend of mine, teacher at Imperial, I met a lot of people, a lot of connections. One of them, Richard Brown, uh, and also a lot of people from NASA, and that helped a lot with the collaboration. And yeah, and then we collaborated, and then we kept going, and now this brought me to here, this stage.
Oh, I love it. I love it. Thank you so much. And you've mentioned some I suppose some support network that you've had along the that journey. Talk us through some of the role models that you have. Talk us through the people that you have met who inspire you, or some of the support networks that you have that you think maybe have influenced your journey. Talk to us about that community, I suppose. Did you have that community? Did you have always supporting friends and family members and teachers, etc.? Did you need to find your own way into the sector? Talk to us about people around you and how they helped or maybe potentially doubted your abilities. Talk to us about that.
So, well, back in school, I had a teacher that really inspired me, a female engineer. She really inspired me. And also, my dad was an engineer. So I think these two things took me to pursue engineering. I think that was very important, having this role model, seeing that I could be like them. And then during my bachelor's, I struggled a bit more with confidence because it was hard, very hard, and I I don't know, I was doubting my capabilities, and but I applied to the masters, and once I got it, and once I met my master supervisor, Peter Vincent, he was amazing. He always believed in me and always pushed me, go to this conference, talk to these people. And I would always felt I'm not ready, I'm not prepared, I'm scared. Imposter syndrome, a lot of imposter syndrome. And but slowly you meet people, you talk to them, you're honest, they're honest, you see everyone's trying their best and trying to figure it out. No one knows everything. You don't need to know everything to present your work and to talk and discuss with people. So that's what I learned.
Yeah,
And yeah.
No, absolutely. I was just acknowledging, I was just agreeing with everything. I was like, yes. And into talking about the imposter syndrome, for instance, I think the best people, highest achievers, etc., they everybody struggles with that. So I think it's just a part of being human. But no, thank you so much for sharing this, Lydia. And I always like to ask questions like this, questions about career journeys and questions about, I suppose, the skills and the experiences that helped individuals. I think here at Flight Crowd, we certainly recognise that no journey is the same. No experience is the same, and certainly the fact that also there's no right or wrong way to get into our industry, get into aerospace, into future flight, and to make a difference. And so we're here to celebrate every journey and acknowledge, I suppose, different ways that people get into the sector and some of the struggles they may have overcome and some of the barriers they've overcome, but also some of the incredible things that they're doing. So, talking about skills, what do you think helped you get to where you are? It could be technical skills, it could be interpersonal skills. Tell us more about kind of the skills that are required to become to get to where you are and to become a an experienced and recognized space engineer or space engineer.
I think more than the technical skills, which of course are important, but I think showing that you're passionate and motivated. I think people really want to collaborate with someone that's motivated and passionate and ready to put in the hard work. I've seen that. And also what I've seen from my experience is that being kind to people is, I don't know, at conferences it just creates these connections. In the end, we're all human, and it makes people see you as a human being, as a person. So of course technical skills are important. Of course, doing high quality research is important and knowing what you're doing, but also just the human part, being being open to talk to people, being open to collaborate, being open to learn, to listen, to discuss. Yeah, I think, and being motivated and passionate about it.
Oh, I love it. I love it. No, these are great words of wisdom, and certainly not everything can be learned at university. Um, no, absolutely. I don't know if you're comfortable to talk a bit about some of the struggles, some of the barriers that you have overcome as well. I know that we always focus on success. We always focus on this is where I am. This is how I got here. And let's celebrate the wins, but maybe kind of reflecting back on some of the things that didn't necessarily go to plan, or that yeah, that you potentially presented some challenges, but you got there anyways. Lydia, do talk to us a bit more about that human part of your career journey.
Yeah, of course. So yeah, during the PhD there were a lot of challenges. I really struggled to feel confident to present my work, so I would get super nervous. I would struggle a lot preparing presentations, and I would be so scared of questions, as I said before, because I felt I didn't know enough, I was not ready. So that was a struggle during my PhD. And also because the PhD is so long, if you push it a lot for a very long time, you can burn out. So that's a reality, and I went through it, and it's not nice because then your motivation and your passion kind of drops. And so it's important to find a balance. I think at the beginning of the PhD, a bit driven by the imposter syndrome and by the I don't know enough, people tend to push a lot to feel enough. And yeah, that's when people usually burn out. So that's been a great learning experience. I think from every struggle, there's a learning experience and something you can later apply to your life in any job, any next project you do. So having that balance is important. And also, as you said before, knowing that every journey is different and not comparing yourself with other people. I think that's also important.
No, and thank you for sharing it. And thank you for being open and being okay to be vulnerable. And I love that mindset, kind of learning from every opportunity, learning from or taking the opportunity to learn from every experience. Let's focus on that's the past. Let's focus on the future. What's the future looking like for you, Lydia? Where are you going to take the research that you've done, the experiences that you've done? What are you going to be doing with this in terms of your next career steps?
So I my dream is to go to NASA. So that's my current plan where I'm trying, but it's a bit hard. I think I would like to continue to do this kind of research. I'm very passionate about it. But at the same time, I really like any kind of aerodynamics. So I'm also very happy to join an eVTOL startup or company. I'm very open to what the future brings. Of course, I have a sweet spot for Mars, so I would love to continue helping explore this planet.
Oh, I love that. Well, in terms of NASA, I think you definitely got closer than a majority of us. You've done a lot of collaborations with them. This is super exciting. But also in terms of eVTOLs and future flight sector, of course, that's primarily what FlightGuide is focusing on. And this is, I know, we've talked about in the past how there's so much in terms of the technical elements, in terms of the thinking, the problem solving, etc., that you can bring into the future flight when it comes to sector, when it comes to drones and sustainable aviation. So there's a lot that the drone designers and engineers, etc., can learn from this experience. So I think there's certainly loads of transferable skills and knowledge that you can bring into the sector. What's the future of Mars looking like, in your opinion? What's the future of space? What's the future of flight looking like? Blue sky thinking, Lydia. No pun intended.
Wow, big
What does
question.
what does it? Yeah, just I mean, we're not. Yeah, we're just talking about it. What do you think, or what would you like for it to be like? Let me word it differently. What would you like for it to look like?
So in terms of space exploration, I would love for it to go much farther. There's very cool ideas on exploring Mars with swarms of drones that also in the future would help humans on Mars. Um, I love any kind of exploration around other planets like uh, Titan, like Jupiter's moons, Saturn's moons. I find it so fascinating. I of it's limited by money as everything, but I would love it to see going forward much more and to be able to see it in my lifetime how we explore all these distant planets and even taking humans out there. I would actually love to be an astronaut. I don't know if I would go to Mars because it's very far, but I would love to go to space.
No, I love that. I think, yeah, I've initially a long time ago I was considering being a pilot, and I thought, no, that's too hard. Being an astronaut, I think, is just another level. So I admire everybody who pursues that journey, being a pilot, being an astronaut. That's definitely no small feat. Um, Lydia, especially for those of us not too familiar with spacecraft design, with when it comes to, you've of course focused on a lot of things, well, simulations and different angles of attack and Reynolds numbers and stuff that some of us will be familiar who've studied aerospace engineering. But if you take it back to how do you even approach designing something for Mars? Talk us through it. for the benefit of those maybe slightly less familiar, I'll put my hand up and say I don't know how to design something that will operate on Mars. I have a much better idea now, but walk us through it. Baby steps. How would you approach that? What are some of the key
So sorry,
considerations?
I hear you very low. So how to design something that would go to Mars?
Essentially, yes. Yeah, let's do
But
that.
in terms of the whole project, like because I'm not a rocket uh, designer or engineer, I know that you put I don't know what exactly you mean, but I know you put in the first Mars mission, for example, they've folded the Mars helicopter inside the Perseverance rover, which is the rover that I showed in one of the first slides. And then they put them in a in an aeroshell, and then they put all these in a rocket, and then they launched the rocket, which has different stages. And actually, the Perseverance rover is this one. So to launch something to Mars, it needs to be at the right moment in time. So I think it's I'm not sure, I don't want to give the wrong numbers, but every few years, the so Earth and Mars are at their closest. So then there's the best kind of path, the shortest path to reach Mars. So you want to launch the rocket at that point, and then the part of the rocket that stays orbits over Earth, and then leaves Earth's orbit, and then orbits around Mars, and then it deploys the aeroshell, which then drops on Mars. And actually, what they're so inside here, they had the Perseverance rover, which is huge, it's like a car. And inside Perseverance, there was Ingenuity folded. So Ingenuity dropped and then unfolded, and then it flew. For the next helicopter, what they're looking at is to have the aeroshell, as the aeroshell goes down, the helicopter would fly away from it before it reaches the ground. Actually, the aeroshell will have some kind of propulsion to slow down, and then the helicopter will fly from it, which I think is very crazy, but very cool as well.
Yeah, no, I love this. Yes, I've probably that question was primarily aimed at me to kind of, begin, even though I have done aerospace engineering at university, we've covered very little on space. So we're focusing primarily on aviation. So I'm like, I need some baby step explanation of what's going on. But also, so how do you think future flight can learn from some of the work that's been done in space? Technical work in terms of approaches, in terms of timelines, collaboration, whatever it may be. How do you think, especially with the world of drones and eVTOLs, what can we take away from the learning and the research that's done in Mars and the research that you've done? What can we what can we take away and put
So I
use?
think many things, and I'm thinking like navigation systems and all these kind of things from my expertise. For sure, also the aerodynamics, because for small drones on Earth, we also have low Reynolds numbers, or even for, depends on the eVTOL as well. So yeah, we can definitely learn. They are also doing micro air vehicles. So micro air vehicles are like insect Reynolds numbers. So definitely we can learn from Martian aerodynamics for it. Yeah.
No, that's great. Thank you. I was going to say there's loads of technical terms as well mentioned, and loads of great concepts. Are there any useful resources that you would suggest for our listeners, for our audience now, for our audience who will be watching the recording, for them to look at potentially in their spare time to continue learning more about the subject if they're interested in? What are some of the key resources?
So for Aerodynamics, I would say the Anderson book. For it depends. There's so many resources. I don't even know where to start.
You should be suggesting your papers, Lydia. That's also that should also be on the list.
Yeah, you're welcome to look at my papers. And of course, NASA has a lot of resources that are for all levels, like maybe some videos that are easier to understand, and then it goes up in technicality. They have also a lot of papers, a lot of resources, and there's also great documentaries, but at the moment I don't know the names of them, but I watched a lot of documentaries for around Mars. So yeah, maybe I can put a few resources afterwards with the video.
I was going to say yes. I think if we can share that with our Engineers Insight group. So for those of you who are new to Flight Crowd or potentially new to our Insight group, usually our webinars are done for our members only, and the Engineers Insight group and the Pilot Insight group are membership opportunities. But we have opened a couple of our first webinars for all. But we will be sharing more of the useful resources that Lydia has mentioned, anything else, and having the discussions on this topic and everything else in our dedicated WhatsApp chat. I'm happy to share more details about our memberships later. But yes, I think that's where we'll probably be able to continue the conversation. But I know, Lydia, there's been one question in the comments that's been waiting. Filippo, apologies, I got there in the end. I got to you. I haven't forgotten. Filippo has been asking that they noticed in the validation slides, 2D and 3D results for low to medium angles of attack are very similar. So let's go back to the validation slides. And then, yes, the
Here,
2D
yeah.
and 3D results for low to medium angles of attack are very similar. Would you see a multi-fidelity approach to be suitable in future development? Now, Lydia, would you mind also explaining what a multi-fidelity approach means?
Yeah, of course.
Maybe
So, well,
starting
first, yeah, of course, of course. First of all, I would like to say, yeah, 2D and 3D results are very similar at low angles of attack, well spotted. And this is because the flow, so even if we are allowing in the simulations for the flow to break down in the third dimension in span, the flow is by nature two-dimensional. So if we looked at a flow picture like similar to this one, we would see that it doesn't vary in span. So it's like repeated. So the flow is inherently two-dimensional, also because this is a very idealized flow condition. So as soon as you put perturbations, maybe it would break down in span. But given that the flow is mostly two-dimensional, at these low angles of attack, if we wanted to optimize these airfoils, which I think is what it means by multi-fidelity. So when you do an optimization process, you can do multi-fidelity optimization process, which means you have different levels of fidelity at different stages of the optimization. So two levels of fidelity would be one is 2D, the other one is 3D. So you are resolving more on the 3D because the 2D one is cheaper. When you optimize, you first use 2D for some loops of the optimization. And then once you get closer to optimum results, then you switch to 3D in case you are missing some details. Also, multi-fidelity could mean maybe you're resolving less by using some kind of modeling, or yeah, that's it. So yeah, definitely we could use a multi-fidelity approach for low Reynolds number. For high Reynolds number, I actually did in my optimization. First I did 2D and then I changed to 3D, and it actually helped speed up things. But we should be very careful when using 2D because it over predicts the results. Still, the optimum airfoils, even if the actual results of lift and drag are wrong, the optimal airfoils are close to the real optimal ones when using 3D. So it helps speed up. Thank you for the question. I hope I answered it.
And if I let us know how if that was okay. But Lydia, thank you. I feel like after this, after the webinar, we'll be able to give everybody a mini MSc diploma or, or at least a workshop on Martian Aerodynamics 101. Yes, thank you for the first mentioning. Thank you. So that's great. Thank you. Team, we've got a couple of minutes. I just wanted to open the floor to any other questions. I wanted to wrap up with a few of things that I wanted to ask Lydia, but also feel free, anybody, if anybody wants to unmute or put something else in the chat as well, now is the time. So I'm going to give you all a few seconds to think if you want to put a hand up, feel free to unmute or feel free to put the question in. Otherwise, Lydia, I was going to ask you a few other thoughts, if that's all right. A few other things I had in my mind. So with oh, there's so much going on through my head. Um, I know we've been talking about creating something to help young people learn about aerodynamics. Where do you think, when do you think is the appropriate time to start? Is there a right time to start learning it? Do you need to be studying engineering to get into aerodynamics? Can you
No.
start at a much younger age? What are your thoughts about aerodynamics in general? There's so much that is being done on aerodynamics when it comes to Formula One, when it comes to just traditional civil aviation, military aviation, all things drones. I feel like it's a massive field that isn't necessarily being spoken about too much. So, when is the time to get involved? How do you get involved? Any of the things that you can suggest for young people to do to kind of get into the sector?
So, well, the first question I thought it was more about when can we start teaching young people about aerodynamics, and I think at any age. Actually, I participated in an event where we were showing kids from 5 years old how helicopters work, and we had these plastic rotors that you could spin, and as the plastic rotor spin, it would go up. And I think they learned a bit about aerodynamics, so I think it's never too early. But of course, in terms of getting into the field, I think at any point, I wish I had the opportunity earlier. I remember when I was at high school, I loved flying, taking planes, and I always wondered like, how do they work? And that's what drove me to study aerospace engineering. But I didn't have to wait, and especially nowadays with so many resources, I think we could create courses for high school students, even younger students.
No, that's I'm glad you've mentioned that because I was going to say I know we've been discussing potentially doing something for those who are completely new to the field. So my question to the audience is, please put yes if you think you'd be interested in joining a course. No details for now because we haven't figured it out, but we would this would really help us. If you're interested to doing a course in aerodynamics, put a yes in the chat, and then we'll see because we've got a couple of ideas. But we've been working with Lydia, we've been working with a couple of our other volunteers at Flight Crowd to think about what else can we do for our community. So we want to listen to you guys. Let us know. I can already see some yeses. Please put more. Or if it isn't aerodynamics, what other fields are of interest to you? Because ultimately, again, we appreciate that everybody in our community is at a different career stage. We've got some who are just looking to join the industry, maybe who's fresh out of university, those who are current young professionals and already starting to work in the field, maybe those who are currently in school and considering their next steps. So let us know if it isn't aerodynamics, what is the field or what is it the topic that you would like to learn more about? Let us know. But I can already see a couple of yeses, so that's potentially a go. Aerodynamics course, go, Lydia. So we've got some work to do after this. But let us know if there's anything else.
Yeah.
No, thank you, team. Lydia, final question from me. We've got your
Oh,
hand up. Oh, yes, Timo's, go for it. You've got your hand up. Please feel free to unmute yourself and ask a question.
Hi, yes. Can you hear me?
Yes, we can
yes.
hear you fine. Thank you.
Hi,
Great.
Tim.
Hi, Lydia. I just wanted to say that was a great introduction to the subject and very well presented. I just had a quick question about maybe you can give us a rough idea of how long these simulations took, DNS simulations, just to like an order of magnitude.
Yeah, sure. So these 3D ones, they took 2 hours. No, sorry. The 2D ones took 2 hours in the optimization on one GPU. The 3D ones took around 20 hours on how many GPUs was it? Maybe 32 GPUs. I should check in the paper. It's written, but something like that. Quite expensive. We were running it on a big HPC with a lot of GPUs.
All right, that's great. Thank you.
No problem. Thanks for your question.
Oh, brilliant. And I can see Ashish has mentioned perhaps ways to break into the industry, sustainable aviation as well, without STEM A levels potentially. Sorry, Ashish, I think this is out of I think this was perhaps to my earlier question, in terms of the courses. Is that so? Sorry, I'm a bit confused. Feel free to unmute yourself and explain it. I think it's my evening brain. Oh yes. Yeah. So okay, so for us to do something looking at kind of helping young people get into aviation without the STEM A levels. Cool, we've got you. Lydia, what A levels did you do? Sorry, you didn't do A levels, did you? You were studying back in Spain. So what was
Yeah.
your background before you got into university? What do you study?
So
What subjects do you do?
yeah, in Spain we have like different options for the last 2 years of high school. So there's like um, artistic, social sciences, technological. I think I'm translating, and I did the technological one. So we would do math, physics, and then the common ones like languages, history, philosophy we had. And
Philosophy is by no means common, but I appreciate that it would be for a different country. No, okay, makes sense. So primarily STEM fields with technical background before you got into university. But I see the request to kind of try and help young people bring I suppose bridge the gap between lack of STEM A levels and getting into the industry. I have some ideas, Ashish. Let me take that away. Let us take it away and we'll come back to you. But that's a great shout. Thank you. Right, Lydia, last question. Any last moment, last thoughts in terms of any advice for young people, anybody who wants to succeed in life, succeed in aerospace, anything else, any last thoughts, any last career advice you would like to share before we wrap up?
yeah, I think the biggest advice I've gotten, which I read about, is to um, expose yourself and kind of create opportunities for yourself. So go to events, volunteer, do things, meet people, talk to people. I think that's where things happen. And many times you will go and nothing will happen. But when it does, it can be like an inflection point in your life and it opens a world of opportunities. So kind of, yeah, stay active and open. And I would say to my younger self, be confident, even if you don't all have it all figured out or don't know as much as you would like to know. It's okay. Yeah, that's the advice I would give to someone younger.
Oh, no, that's brilliant advice. And I can see Esther has mentioned this is what happened when I joined Flight Crowd. Thank you so much. And yeah, absolutely. I completely agree, Lydia, with everything you said, Neshes. Thank you. It means so much. I think it's certainly great things happen not to those who wait, but to those who act. So thank you to all of you for coming here, for playing an active role in your career, in your life, taking an active step towards your future, joining us, joining this discussion, putting your questions in the chat, learning. And I really hope that you will continue doing this within Flight Crowd and much wider. Never stop learning, and never forget that you're not alone, that we all have our challenges, that we all have things that we, when moments of doubt, moments of lack of confidence and imposter syndrome, but you're not alone. And please, please, please stay in touch with us. We've got a brilliant community where people are on the same journey as you, but we're not forgetting anybody. We're here to support each other, and we're here to make a world a better place. Thank you so much, Lydia, for all the work that you are doing with us at Flight Crowd and wider. All the best of luck. I know we're going to see you many a time because you are, of course, the co-chair of our Engineers Insight group. Thank you to our audience. Fantastic webinar, and I hope you have a great rest of your week, and we will see you
Thank you so
shortly.
much.
Thank you all. Take care. Speak soon.
Bye bye.